On April 10, 2026, Artemis 2 splashed down in the Pacific Ocean, bringing to a close the first human flight to the moon in over 50 years. About 14 hours before splashdown, I recorded this faint dot moving through the sky on film with my 11-inch Celestron Nexstar telescope. These photographs were taken using Cinestill 800T film pushed 2 stops in development. Although these photos look unremarkable, this completes a goal I had set for myself when the Artemis program started, which was to capture humans heading to or from the moon on film the way it had been done over 50 years ago by amateurs who documented the flights of the Apollo program. Some would say that these photos are not only unremarkable, but also unverifiable. How can I possibly know that this is the Orion spacecraft?
I heard the same thing about the Apollo missions, all right? I had one person, and we'll put it up, because I simply asked a very simple question. Is there any group of private citizens? There's a ton of observatories out there, right, Aaron? There's a ton of there's a ton of high-powered telescopes. I said, is there any group of individuals that are visually tracking this thing start to finish to verify any of it? And I mean, first I just get attacked. Then, of course there are. There aren't. Okay, there is zero. There is one site up called Astronomy Live. I'll put it up for those that will visually watch this later. That when you look at what they put up, all right, there is, I mean, no actual way. Don't get me wrong. You watch movement in stars. We're watching it here. But there's no way to verify what you're watching is Artemis, right? At all. Zero. Okay? Like, I'm not even saying there's not a rocket out there. I absolutely believe there's a rocket out there. I believe that there are people in space. I believe space exists. I know you know this, Aaron. But boy, oh boy, those are the big attacks, right? I've got people in there and like they're coming at me like I'm a flat earther, and I'm not.
So how do I know that this little dot really is Artemis 2? How do I know that it went to the moon and came back? That is exactly what this video will be addressing. But first, let's back up to the launch. About 4 hours before launch, the crew arrived at the pad. Here we see Commander Reed Wiseman leading his crew to the crew access arm to board their capsule. Following him is Canadian astronaut Jeremy Hansen, followed by Victor Glover and Christina Cook. Across the river in Titusville, Reds Rhetoric was filming this scene with his telescope, and we can see Wiseman leading the team, followed by Jeremy Hansen, and then Victor Glover as they begin crossing the crew access arm. Hansen stops to look over the railing, and we see that reflected in Red's footage. Then, finally, Christina Cook brings up the rear, followed by Bill Owens, closeout crew member number 3. During the launch, I noticed something unusual next to the rocket. It looked like a little moving star down and to the right of the capsule, and it appeared to be moving, if anything, up and towards the rocket. Did you see it there? It was real short. Let me play it again at 50% speed, and once more again at 25% speed. Now, at first, I had no idea what this was. I had never seen this particular kind of artifact before during a launch. But I have to give credit to David Hash for pointing this out, and it's related to this shock wave that you see moving down the capsule a few seconds before. This phenomenon has been previously noticed during shuttle launches, where light from one of the engine plumes can be refracted through a shock boundary and create the appearance of a star-like object near the vehicle. This phenomenon has also been observed during Falcon 9 launches, like this video from the launch of SES-12. You can see the shock boundaries there, and you can also see star-like apparitions near the rocket. The core stage of the SLS rocket did its job and put the vehicle on a suborbital trajectory with an apogee of about 2,300 kilometers. After systems were checked out, the ICPS raised the perigee so that it would stay in orbit, and then did an apogee raise burn to put it in an elliptical orbit with an apogee now of about 71,000 kilometers and an orbital period of about 24 hours. The crew then separated the Orion spacecraft from the ICPS, which you can see trailing the Orion spacecraft in this time-lapse that I recorded later that night and live-streamed on my channel. This is the time-lapse that Jason was showing before. But we can learn a great deal about what this vehicle is from analyzing these images. By measuring the coordinates of the object over multiple points in time, we can solve for the orbit, and that's exactly what I've done here. Now we know the rocket launched almost due east, so its inclination should match roughly with the latitude of the launch pad, and that's exactly what we see here, with an inclination of about 28.3 degrees, about 0.3 degrees within the latitude of the launch pad 39B. About 24 hours after launch, when the spacecraft reached perigee again, and at about the latitude of the launch site, they used the main engine in the service module to burn for the moon, called the TLI burn. I simulated this burn in Orbiter Spaceflight Simulator, planning for a free return trajectory around the moon, just like the real mission was planning to do. The tracking that I did from the first night was used to put the spacecraft in the simulation, and then after I simulated the burn, I extracted the location from the simulation and used that to predict where I should see the Orion spacecraft in the sky if they were really heading for the moon. Starting from those coordinates, I conducted a search for anything that moved, and finally, I found it. You can see it here near the center of the frame, moving relative to the background stars. I continued to track the object for the rest of the stream, and you can see it moving here from left to right. Once again, I measured the position of the object over time to solve for the orbit. Now, a single night's observations from a single location produces a crude orbit determination, but it's enough to get it in the telescope again the following night. I was within about 5 arc minutes of where it ended up being. Using these post-TLI orbital elements, I predicted where I would see it in the sky about 24 hours later so that I could set up my telescope and track it again. I also tracked it from a telescope in Utah on the iTelescope network so that I would be able to get parallax measurements and directly measure its distance. The parallax measurement I conducted 3 days into the mission revealed that Artemis II had an altitude of over 325,000 kilometers, which is about 86% the average altitude of the Moon. You may well be wondering how I can know that this is Artemis II. After all, just because I found something moving on April 4th doesn't necessarily mean it was Artemis II. How do I rule out some other random asteroid that just happened to be in the area I was searching? Well, what we can do is take the observations from April 4th and April 5th and solve for the orbit and determine a much more precise orbit because we have a longer baseline of time of those observations. And we also have observations from a second telescope over in Utah. Now, as luck would have it, they didn't perform any trajectory correction maneuvers between April 4th and the April 5th observations. This allowed for the residual between these observations to be very small. The mean residual, when combining these observations, is only about 1 arcsecond, so it's a very good fit. The residuals you see in the middle of the screenshot in parentheses are future observations I haven't shown you yet, and they're excluded from this analysis, but this shows how well they would have fit with the orbit we've determined so far. Now, up at the top, the perigee time indicates the time it was last closest to Earth, and this works out to 2350 Universal Time on April 2nd, which is exactly when the TLI burn was happening. We can also see down at the bottom, circled in red, that the latitude of the spacecraft around the time of the TLI burn matched very closely with the latitude of the Kennedy Space Center of about 28.5 degrees. Again, this is because the rocket launched due east, and because of the way SLS is designed, the core stage of the rocket starts to do some of the work of extending the apogee or point furthest from Earth away from Earth, so it ends up in an elliptical orbit right away, unlike the Apollo program that went into a circular parking orbit. This also means that when they start performing the TLI burn, they're doing so once again at about the same latitude that they launched from, 28.5 degrees, because that is the point that is closest to Earth and where it is most efficient to burn to extend the apogee on the opposite side of the orbit. Now, because the apogee is on the opposite side of the orbit, that also means they are going to the Moon at a time when the Moon's declination is highly negative, and that's because of the way SLS is designed, and because the core stage needs to do some of the work of extending that orbit out to the Moon. So all of these points of evidence all point to the fact that this is Artemis II, that it was last closest to Earth at the time that the TLI burn was happening, and that it was at a latitude that matched the launch pad, because that's where it launched from, and it launched due east. We can also plot the orbit and see that it corresponds to a free return trajectory. It leaves the Earth, heads out to the Moon. The Moon reaches the position of the spacecraft, and the spacecraft passes behind the Moon and then falls back to Earth. This orbit wouldn't make any sense for a natural object. It comes from the Earth, heads out to the Moon, and then returns to Earth to enter Earth's atmosphere. But that's exactly what we expect for Artemis 2. As further verification of Artemis 2, we can also take the photos from the mission, like this photo of Earth taken on the night side of Earth illuminated by the Moon, and we can look at the date timestamp of that photo and see what should have been seen from the perspective of Artemis 2 based on my tracking of the spacecraft. We can take the longitude, latitude, and altitude of the spacecraft predicted by my orbit determination and feed that into a program like Celestia to see what we should see from that time and that point in space. Sure enough, we see that it's a match. You can see the continents of Africa and South America appear the same in Celestia and in the actual photograph. And if you look at the stars surrounding the Earth in this long exposure, you can see that Earth is positioned relative to the stars almost exactly the same in the Celestia simulation as it is in the actual photograph. And of course, once again, the Celestia simulation is being driven by my prediction of where the spacecraft should have been from tracking it on April 4th and 5th. We can also go forward in time to April 6th and the lunar flyby and predict what should have been seen from the spacecraft at the time that photos like this one were taken. Once again, I used my orbit determination to predict the latitude, longitude, and altitude of the spacecraft at the timestamp of this photograph and entered that into Celestia, and sure enough, we see the exact same view of the Earth preparing to set behind the Moon. Here's another one of my favorite photographs from the mission, and note that you can see the outline of Australia there. I took the timestamp from this photo and used it to generate another prediction using my orbit determination and fed the results into Celestia, and once again, we see that it's a match. Following the lunar flyby, I continued to track the spacecraft as it began returning to Earth using telescopes around the world on the iTelescope network. This one was T59 in Australia. Now, due to all the glare from the Moon, you probably didn't see it there, but it was at the bottom of the edge of the field of view. Here it is zoomed in and cropped in on the spacecraft. You can see it streaking through the center of the field of view. Now, the reason it was at the edge of the field of view was partly due to the fact that they did a course correction maneuver early on April 6th, and now on April 7th, the spacecraft has deviated a bit from its previous orbit that I determined. So, I'm able to use these observations to begin a new orbit determination. Here it is on April 8th, 2026, using telescope T72 in Chile. And here it is from telescope T32 in Australia, and I will zoom in so you can better see the streak of Orion against the background stars. Here it is once again from telescope T72 in Chile on April 9th. And finally, once again from T72 in Chile, here it is on April 10th, re-entry day. Now, I was also live streaming from my telescope the morning of April 10th, and this was recording from the end of that live stream, which brings us back to the beginning of the video and that little dot that I captured moving on film. Immediately after the end of the stream, I took off this video camera and replaced it with my mechanical film SLR camera, an old Minolta SRT-100. We can overlay the stars from the last few minutes of this stream's video on top of the pictures that were recorded on film, and project out where we should have seen the Orion spacecraft minutes after the stream had ended. Keep in mind that this clip I've been playing has been accelerated 4 times and has been inverted to match the orientation of the film. Now when we look at the dot that was moving on film, and we overlay some frames from the last few minutes of video matching up to the positions of the stars on the film, and extend a line through the points of where Orion was on film, we find that it intersects the dot that we saw moving on the film, showing us that this was indeed a continuation of what we had been seeing move during the live stream. This is the Orion spacecraft on film. Using a couple of pictures of Artemis 2 that I took with my scope on the re-entry day, along with some observations from Chile, I was able to predict the re-entry path. First, we can see the point at which the spacecraft's eastward velocity starts to exceed the Earth's rotation, which causes it to appear to sharply turn to the northeast. and we can see the point where it should have hit the atmosphere just east of the Hawaiian Islands as it was heading northeast towards San Diego, where it splashed down. My astrometric measurements, along with the orbital elements I calculated from my observations, will be available as a link in the video description. Today we've learned how I've been able to use just that moving dot to confirm that this really was Artemis 2, that it launched from Florida, that it went around the moon, and came back and re-entered over the Pacific Ocean, exactly as NASA said. Thanks for watching, and until next time, clear skies.